Welcome back. In this very short video, we just come back to the notion of area of planar regions that we started our story with. So again, we have in our mind the running assumption on functions that we are concerned with, that is f is a real valued bounded function on a closed interval ab. Now, first let us try to understand what happens in the case when f is a non-negative function. That is, if x is bigger than or equal to 0 for all x inside the interval ab. We say that the region RF is this region. Let me tell you in a while what is the description of it. We say that the region RF has an area, the shaded region has an area if f is integrable on the interval AB, and in such a case we will say that the area of RF is equal to integral AB of fx dx. Now it is very intuitive because we have developed the notion of Riemann integrability based on these ideas only. So in this case, it has to match with the notion of area. Now what is RF? So here is our graph of the function y equal to fx. Here is my x equal to a. So I take the line, the vertical line x equal to a. I draw the vertical line x equal to b. So the RF is the area, is the region that is bounded above by the graph of the function y equal to fx, to the left by the line x equal to a, to the right by the line x equal to b, and at the bottom it is bounded by the x-axis. The area of RF, if f is integrable, is given by simply the integral of f defined from x equal to a to x equal to b. We have seen that if f is bigger than or equal to 0, then integral of f should be bigger than or equal to integral of 0, which is 0. So area of RF has to be bigger than or equal to 0. You may try to convince yourself that this is indeed the case, that integral of 0 is 0, which can also follow from the integral of constant functions. So you remember that we have considered the functions fx equal to c for all x inside the interval ab, and you just put c equal to 0 and find out that the integral indeed turns out to be equal to 0. Last but not the least, what happens when this condition is not there? Pictorially, we may get a graph of a function y equal to fx as it is given in the picture. So the whole region, this one, and this one, here is RF, and let us see how do we what do we get in such a case. So here, suppose that f and g are two integrable functions. So for the time being, just forget about this picture. We will come to this in a moment. So suppose that f and g are two integrable functions. We claim that then so are the functions, the first one being maximum of f and g, and the second one minimum of f and g. How the functions max fg and mean fg are defined? Algebraically, it is defined to be f plus g plus modulus of f minus g divided by 2, and the mean is defined as f plus g minus modulus of f minus g divided by 2. What do these things mean pictorially? Let me use some other color. So suppose that the graph which is depicted in green color shows the correspond to the function y equal to gx, and the picture in blue color corresponds to the graph of the function y equal to fx. Then what is the maximum of these two functions? Pictorially, the maximum is where the point where we are taking just the point is maximum. So at every point we compare what is bigger, fx or gx. So if we will get exactly this curve, and what is the minimum function, let me draw it in black. So minimum function is going to be the rest of the part. So our claim is that if f and g are two integrable functions, then so is max fg and mean fg. How do we show that? So let's do it once, and we will not be bothered with this again. So if g are integrable, so that means we have already seen that f plus g is integrable. We have also seen that f minus g is integrable, and if f minus g is integrable, then modulus of f minus g is also integrable. So this gives us that f plus g plus modulus of f minus g, this is integrable, so this is integrable. And since half is a constant, if I multiply this whole thing by half, then the resultant is also integrable. So f plus g plus f minus g divided by 2 is integrable. But this was exactly what the what the maximum of f and g were. Similarly, we can prove that minimum of f and g, this function is also integrable. Now let's come to this very particular case where f is an integrable function which is not necessarily bigger than or equal to 0, not necessarily non-negative. So in that case we can come up with two functions, f plus and f minus. What is f plus? F plus is maximum of f and 0, f minus is minimum of f and 0. So in this picture what we are going to do, the maximum, so what is f plus? So f plus is going to be exactly this thing, and what is going to be f minus? So let me put it in black. So f minus is going to be, so this is the minimum function. Now if I put a minus here, so then you will see that you will get a reflection of the region below over here. I hope this is clear. But now if I want to integrate f from a to b, we can see that this area will contribute as positive to the integration. This area, this shaded area, will contribute to again some positive thing in the integration. However, you can see that the rectangles that we come up with, MIF, and so here MIF will always be less than or equal to 0, small MIF is always be going to be less than or equal to 0. So in particular this area will contribute something negative to the integral. So as we can see that the integral of fx dx will be equal to area of Rf plus, so this is this region union this region, minus the area of Rf minus, which is this region. So how the integral is calculated? This is area of this plus area of this minus area of this, which matches our intuitions. You may now realize that up till now we have not used at all the notion of differential calculus. However, you may have had the intuition at the beginning of this course that differentiation is somewhat, in some sense, an inverse to the notion of integration. Of course, we have seen such kind of things when we read about indefinite integrals in our high school mathematics. But you may come to appreciate up till now in this course that the theory of integration that we have taught you till now is totally independent of the notion of differential calculus. In what follows, we will produce, we will show you, or we will prove to you a fantastic theorem which is called fundamental theorem of calculus, which will come in two parts, and it will show, is it will establish a very nice relationship between integral calculus and differential calculus. Till then, goodbye.